Okay, it's 10 o'clock here in GMT time. Actually, that confused us because we've got a summer time, which is 1 hour ahead of time. Anyway, so good morning and good evening in Japan. We are ready to start session M3, which is on inspection. There are 3 papers. The one is about cleaning residual water with a mechanism in sewer pipes before inspection can take place. The other one is about communicating with a mobile robot that is immersed in an oil storage tank, doing inspection of the floor of the tank. And finally, the third paper is about inspecting wind blades with a robot that climbs on the tower to reach the blades. So if you have the first speaker for the first paper, I don't know who that is. Is it Kosuke Uchiyama? Hello?
Sorry, can you hear me?
Yes, we can hear you now.
Oh, thanks for the introduction. Can you see my presentation?
Yes. Are you Kosuke?
Yes, I'm Kosuke Uchiyama.
All right, please introduce yourself and start your presentation.
Thank you. I'll start my presentation. I'll give a presentation titled Residual Water Removal Mechanism for obtaining clear images with sewer pipe inspection robot. This is my presentation agenda. First, I'd like to present the introduction. Storage is an important infrastructure facility in the world. However, the number of aging sewer pipes that have exceeded their useful life of 50 years is increasing. Aging pipes can lead to serious accident as figured 1. So regular inspection of the pipe inside is necessary. Pipe inspection is performed using camera images obtained by special devices. Existing special devices include automated robot like the figure 2 and the push-type endoscope like the figure 3. However, considering that sewer pipes are thin, long, and complicated, the devices have problems. Automated robots have difficulty inserting into small diameter pipes and have difficulty passing through bending pipes due to their high rigidity. In addition, as shown in figure 4, the push-type endoscope causes friction in the bending pipe, which increases the force required to push in. So it cannot conduct long-distance inspection. Therefore, in this study, we established the inspection method for thin, long, and complicated pipes. The sewer pipes that are difficult to inspect with existing devices are the pressure pumping method pipe. Its features are thin, long, and complicated. So especially we focused on the pressure pumping method pipe. In the previous study, earthworm peristaltic movement was focused on. Peristaltic movement is shown in figure 6, and it has 2 advantages. First, it can proceed in a small space because it requires only space for radial expansion and contraction. Second, it can generate high traction force because it has a large contact area with the outer wall. Based on this peristaltic movement, we created pipe inspection robot PEW-RO V, shown in figure 7. This robot successfully inspected on actual pipes. However, if there is water in pipe, inspection by the camera image is not possible. When the water remains in the pipe, it looks like figure 8. In the residual water, camera images are unclear. So the purpose of this presentation is to develop a mechanism to obtain clear images regardless of residual water. Considering the development of the mechanism, there are two problems. First, the water is clear, the camera images are unclear in the residual water. So it is difficult to clarify the camera image by filtration. And we decided to use a water suction pump to remove residual water from the water intake. Second, if the robot has only one water intake, the water intake will leave the water due to self-rotation as figure 10. For this problem, the water suction intake always need to kept submerged in water. Therefore, the mechanism must solve these problems. Second, I'd like to present the residual water removal mechanism. An overview of the inspection robot mounted with residual water removal mechanism is in shown figure 11. As a residual water removal mechanism consists of a water suction pump and a water suction unit. About this, the water suction pump must be capable of sucking up residual water at the length of 60 meters and a height difference of 4 meters without priming water. And the water suction unit must be capable of sucking water to a level lower than the camera when the head is rotating. So these two topics will be presented. First, let's talk about the water suction pump. From among the many pumps, a vein pump was selected. A vein pump is kind of volumetric pump like figure 12. We chose it because it can suck little water without priming water. The vein pump used in this study is shown in figure 13. This pump is connected to an electric door to drive it. In this slide, I show the pump's basic characteristics. Figure 14 shows the relationship between the rotor speed and flow rate. As rotation speed increases, flow rate also increases. Figure 15 shows the relationship between pump location and flow rate. As the distance between pump water intake and the pump increases, the flow rate decreases. So in the experiment, we kept the rotor speed constant and mounted the pump just behind the robot so that the pump and water intakes are close together. Next, let's talk about the water suction unit. The water suction unit must be capable of sucking water until the water surface is reduced to 47 millimeters or less when the robot rotates on the pipe axis. Based on that, water suction unit was developed shown in figure 16. It has two device points. First, two water intakes are provided and their tips are made of silicon tube. From this, if the robot rotates on pipe axis, one water intakes will land on the water. Second, silicon tube and the water suction hose connected through the Y-shaped joint. From this kinking of the suction hoses was prevented from the robot progresses. For more information about where to mount of this unit, as shown in figure 17, we decided to place the unit between the second and the third unit for the passages of a bending pipe. Third, I'd like to present experiments. We conducted functional verification experiment of the water suction unit. Its purpose is to verify that the water suction unit is capable of handling self-rotation and solid sludge in residual water. The figure 18 shows this experimental environment. We conducted water suction in two conditions. First, it sucked 7-liter tap water. Second, it sucked 7-liter tap water with 2,500 balls, assuming solid sludge. The experiment was conducted by rotating the robot on the pipe axis. In figure 19, we put cloud tape at the head part to experiment with each angle. The table 1 shows the angle of the head part when each color comes to the top. The figure 12 shows the state of the water suction unit at each angle. The water suction experiment is conducted once at each angle. After water suction, we measure the water level in the pipe. The figure 21 shows the water suction of tap water, and the result is shown in figure 22. Water suction time is about 6 minutes, and successfully lowers the water level in the pipe to below the target level of 47 millimeter on all 3 times. Therefore, as the target is achieved by sucking water from the water suction unit at an optical optional angle when the robot rotates on the pipe axis. The figure 23 shows the water suction of tap water with air balls, and the result is shown in figure 24. As in the prior experiments, successfully lowers the water level in the pipe as shown as figure 24. So therefore, achieve the target in water suction of residual water with solid sludge. Finally, I'd like to present conclusions. As summary, we developed a residual water removal mechanism for pipe inspection robot, and the robot successfully sucked residual water enough for the camera to be exposed from the water. As the future works, the mechanism to remove residual water containing a highly viscous liquid sludge that is difficult to filter with the existing joint attachment will be studied. Thank you for listening.
Thank you very much for an excellent presentation. We now go to a question and answer session. Any questions?
Can I ask a question, Professor?
Yes, please go ahead.
Thank you very much for your presentation. Just want to know what sort of cameras you are using, and what's the what sort of defects you are targeting with that.
Oh, sorry. Could you tell me one more time?
Are these special cameras which you're using, and what sort of defects you can detect with those cameras?
You asked me why the camera is in the head part. Is it?
No, the question is, what type of camera are you using, and what kind of defect are you looking for?
Thank you. Thank you for asking question. Sorry, I don't know about this camera in detail, but this camera is like endoscope camera, but this and not So it is different or different of endoscopes. It can move, use peristaltic movement. Is it okay?
So what kind of defects are you looking for? Are there cracks in the pipeline, or are they caving of the pipe, or is it something else? Maybe clogging the sewer, something getting stuck in there.
We use this camera, and from the we watched camera images, and where is there a break or a crack in the pipe, and we detect from the camera images.
Okay, if you were using ultrasound, it would be advantageous to have water in the pipe, wouldn't it? Because then you would have a couplant to couple your ultrasound to the pipe wall. You could look for cracks that are maybe even hidden.
Yes, we detect the crack where is crack and a break part from this camera, and as future works, we use any other detection methods that is on study.
Okay, thank you for your answers. Our time is up, so we will move to the next paper now. Thank you very much.
Thank you for the listening.